Okay, this video is about the periodogram. We didn't cover the periodogram in the book, but as you read time series texts and time series literature, you may see the periodogram mentioned. So I wanted to do this video concerning the periodogram so you would know what's going on. It's nothing new. It's actually the sample spectral density evaluated at harmonics of the fundamental frequency. Well, we know what the sample spectral density is, but we haven't defined the harmonics or the fundamental frequency. So I'm going to define these topics, and then we'll talk a little more about the periodogram. So let's remind ourselves that sample spectral density is equal to 1 plus 2 times the sum. K goes from 1 to n minus 1, rho hat sub k, sample autocorrelation, times cosine 2 pi fk, and that's for f less than or equal to 0.5. So some things to remember about the sample spectral density. One thing was it was very erratic in behavior, and we didn't really use that as our measure of the periodic behavior. We actually wanted to smooth that and use the Parsons smooth version of the spectral density. So we need to talk about harmonics and fundamental frequency. The fundamental frequency is 1 over n. So that would mean the fundamental frequency is associated with a period of 1 over n, or n, the length of the series. And then the harmonics are k over n, where k is an integer. And we looked at harmonics for k over n is less than or equal to 0.5 because of the Nyquist frequency. So if n is even, and I didn't say it, but the k's are integers. If k is even, then if n is even, k equals 1 out to n over 2. And if n is odd, then k goes from 1 out to n minus 1 over 2. So we see that the spectral density technically is defined at every frequency between 0 and 0.5, whereas the periodogram is only defined at the harmonics of the fundamental frequency, these finite number of points. So when we plot the spectral density, we plotted a smooth curve, but when we plot the periodogram, we plot vertical bars. And so let's suppose I had a realization of length 10, and so I'm going to draw a periodogram. And so those are the values at which I'm going to evaluate the spectral density in essence. So suppose I had a data set that had a period of about 0.2, then maybe the periodogram would look like this. It would be vertical lines at each of the harmonics, and probably it's going to be erratic like the spectral density would have been. So that's a plot of the periodogram. Now, you can actually get the periodogram using TSWGE. The function plots dot sample dot WGE has an option or a parameter called periodogram. The default value for that is false, and so when we've been using plots.sample.wge, we've been using the default option and not plotting the periodogram. But if I specify periodogram equals true, Then plots.sample will plot the data, sample autocorrelations, smooth spectral estimator, parson, and the periodogram. So that's the periodogram. Nothing new, but it's something that you may see as you do your reading.